Okay, thank you everybody for coming to this week's seminar. So this week we have a guest from Georgia Tech, Aiya Kuchukova, and she's going to be talking about sampling related to graph coloring and beyond. And I'm very excited to hear what she has to say. So whenever you're ready, Aiya, please feel free to start.
Hello, everyone. Happy Fool's Day. Um, I'm a third year student at Georgia Tech, and I'm advised by Will Perkins. And I should say that everything in my talk is going to be a joint work with Will Perkins and Xavier Povill. And today I'm going to tell you about my probably most favorite projects of recently. And I think it's like my favorite project because it's the project where I got to see the intersection of statistical physics and sampling algorithms and graph theory kind of very naturally coexisting and producing something really cool. And I hope that I'll be able to share that with you. Um, this talk does not assume any knowledge of statistical physics or sampling. So if at any point you have questions, please ask questions, maybe out loud, because I don't think I can see the chat when I share screen. But yeah, so let's start with something that we all really like, naming colorings. So, okay, we know that for a graph with maximum degree delta, later we're going to call it delta bounded, Q colorings exist for Q bigger or equals than delta plus 1. Um, and so the big question that you can ask yourself is, can we approximately sample a uniform Q coloring for a delta bounded graph where Q is bigger or equals than delta plus 2? I'll explain where delta plus 2 is coming a little bit later, but let me explain the keywords first. So what does it mean to approximately sample? So we want an algorithm that will output random colorings with some distribution that is very close to uniform. And there is a rigorous way to define close, like variation distance, for example, but I'm not gonna really pay attention to that now. Just know that there exists, a rigorous metric by which we're measuring distance between probability distributions. So, okay, what are some tools for discrete sampling? It's usually Markov chains. And particularly a Markov chain called global dynamics. So it appears in a lot of different places, and especially physicists really like it because it connects to some physical phenomena happening. And it's very simple. So you start with a proper coloring, and then on every step, you choose a vertex V uniformly at random. And then for a vertex V, you look at its neighborhood, and you forbid all the colors of its neighbors, and everything else is your available colors, and you just pick one uniformly. So very simple, very intuitive. What we can say immediately is that if you have delta plus 1 colors, your state space is not necessarily ergodic. Well, what that means is it is impossible for Glover to move between colorings. Like, let me give an example. If you have a clique of size delta plus 1, then every vertex has delta neighbors. And so you already are using all delta colors, and so the only available color to you is the last one, which means on second step, you're always going to pick your own color over and over and over. So you never move from this coloring. That means that all colorings are isolated from each other. So there is no way for global dynamics to move in between them. So that's why we don't really look at that case. However, for number of colorings that are colors that are bigger than delta plus 2, uh, it is like ergodic, and everything's very nice. It's not hard to show that the station distribution is uniform. That means that if I run this process for long enough, at some point I will converge to the uniform distribution. And that's great. I mean, and then the question is like, didn't we answer my question at the beginning? It seems like we have an algorithm. It samples like almost uniform colorings. And so the reason we don't think the question is answered yet is because we would want something effective. We would want some kind of guarantee that after a certain amount of steps, I am actually epsilon close to my target distribution. So, okay, that inspires a definition of mixing time. So I'm going to say that T epsilon is the mixing time such that every step after that, the distribution my algorithm produces is epsilon close to my target one. In this case, uniform distribution. Are there any questions by now? Cool. So note that we actually can just forget about epsilons because we know that T epsilon is only a constant away from T1/4. What that means is if I know how to get myself 1/4 close to the uniform distribution, I can just repeat my algorithm like log amount of times and I will get epsilon close. So I don't care about epsilons in this talk, just assume every epsilon is like 1/4 or something. Um, okay, what are some easy lower bounds? Well, I told you that the first step is choose a vertex uniformly at random. By the coupon collector argument, for us to visit every single vertex, I would need at least n log n steps, right? And I need to visit every single vertex because otherwise, like the color of the vertex I didn't visit just gets inherited from the color I chose at the beginning, right? So it's not really random. Okay, so that was simple. But is that tight? So the really big conjecture, that's just folklore because I really don't know who started that conjecture, is it is possible to approximately sample a uniform Q coloring for Q bigger or equals than delta plus 2 with global dynamics in n log n time for delta bounded graphs. Okay, so there's been a lot of really impressive progress on that, but the problem is hard. So the first big result on that was in 1995 by Jerome, and he was able to prove that global dynamics mixes in n log n time, but he requires 2 delta plus 1 colors. And that kind of seemed like a very natural barrier. It was really hard to get past that. And then Vigoda in 2000 was able to get n square log n time for 11/6 delta colors, which is approximately like 1.833. And then 18 years later, two teams of researchers, so Delcourt, Perrenau, Postel, and then Chin and Moitra, they were able to get n square log n, and they were able to draw the number of colors by epsilon. So here epsilon is constant, I think. And so, you can tell the problem is really hard when it takes 18 years to get your bound, like, smaller by an epsilon. And there was a really cool, impressive recent paper by Carlson and Vigoda, and they were able to show n log n mixing time for 1.809 delta colors. So the problem is really interesting. Everybody really likes it. Everybody wants it to be solved. It's hard. But this is for the general class of delta bounded graphs. There have also been a lot of improvement for specific classes of graphs, which I'm not going to really go into, but the general intuition is that it's simpler to prove this kind of results if your graphs are very sparse. And so I feel like a very valid question to ask at this point is, we're trying to sample colorings. It seems to be hard. How well can we control the colorings that we want to sample? And I'll try to define in this talk one way that I think is a natural way to try to control colorings. And I'm going to say that I have a vector n, and G is n colorable if there exists a proper Q coloring with n1 vertices of color 1, n2 vertices of color 2, etc. And so given the vector n, is it possible to approximately sample a uniform n coloring? So let me give a case, like subcase of that. For example, equitable colorings. So we're going to say a K coloring is an equitable coloring if all color class sizes are n/k floor or ceiling, which means that all color class sizes basically differ by at most one. Hartnell and Samerdi in 1999 proved that any delta bounded graph has an equitable delta plus 1 coloring. And there was a very short and elegant proof by Kirsten and Sasha in 2008. And it also gives a polynomial time algorithm to construct such. Okay, so this is what's happening in like graph theory world. And in the algorithm way of looking at this, what we're trying to do is we're trying to sample with some kind of global constraint. And so what is this, like the history of trying to sample colorings? I don't know how to get rid of this. How to sample with constraints in other models. And typically independent sets is where everybody starts because we know a lot about independent sets, at least in terms of algorithms. So let's look at a physics model that basically yields a lot of really cool sampling algorithms, and it's called hardcore model. So what it does, it's a generative function, basically. It's called partition function by physicists. And what it does is it takes a family of independent sets, and it's a sum over all independent sets, where the weight is your parameter lambda to the power of the size of your independent set, right? So let's play with this a little bit. If I take lambda really large, that means I'm giving more weight to independent sets with very large size. If I take lambda very small, like close to zero, it means that I'm giving more weight to independent sets with much smaller size, like almost empty. If I take lambda equals to 1, all the weights of my independent sets are just equal to 1. So like I prefer them all equal. And moreover, if lambda is equal to 1, the partition function just counts the number of independent sets. So it's generally really hard to to compute it exactly, but potentially can approximate that. Okay, it also yields a Gibbs measure. So a Gibbs measure is a physicist's beloved probability distribution because it can be defined for every single statistical physics model. And it's very simple. Let's say I have a random independent set, and the probability of a particular independent set to be that random independent set is just the weight of that independent set divided by the sum of all independent sets together, right? Which just happens to be the partition function. So you can see that if I make lambda very large, I will give more probability of appearing to weights to independent sets that are very large. So you can also study really large independent sets in that way. And it's a really useful model, like almost all independent set sampling uses that. Or for example, like the recent breakthrough on the sphere packings number was achieved using this model. And we also know a lot about the model. Okay, so what do we know is possible? We know by weights that it is possible to approximately sample independent sets for all lambdas below this critical value. And also when I say approximately count, I mean estimate the partition function, because estimating partition function and sampling is in a lot of models an equivalent task. So Davis and Perkins were able to show that there exists a critical lambda. So if you take lambda less than that critical lambda, and you try to sample independent sets of size lambda times n, you can get a polynomial times sampling algorithm. But no sampling algorithm can exist for lambda bigger than lambda critical. So it's like this really interesting behavior where your algorithms are really nice up until a point, and then nothing is possible beyond that point. And then in a really cool work, I think it was like the best Fox paper that year, but I don't quote me on that, by Jane Mitchell and Van Vaughan. They proved that a down-up walk samples approximately uniform independent sets of fixed size in n log n time, but they have to get independent sites, they have to get their size less than whatever the critical threshold here is. And that was really nice because I think there's also a lot of push toward trying to prove sampling algorithms with easier and more natural Markov chains, and in this case, down-up walk is. And they also use hardcore model. So some other results where you can try to sample with global constraints is, for example, with Marcus Papik and Will Perkins and Corinne Yap, we were able to show a dynamical threshold for dynamics called Kawasaki dynamics. Don't worry if you don't know what it is. But basically what we're able to show is that in a certain range of parameters, we have a very natural dynamics mix in n squared log n time, and like almost everywhere to the right of that, it's gonna mix exponentially slowly. So you also get this like interesting kind of behavior. And this is really, really cool just because here we're doing this for statistical physics model called ferromagnetic Ising model, and we put a fixed magnetization constraint on it, right? And the interesting thing is, without this constraint, it is possible to sample anywhere in the parameter regime. So like suddenly when you put a constraint somewhere, you can introduce a new kind of behavior. So some other results is, for example, people can show that, Jane and Misger can show that like down-up walk mixes in polynomial time on matchings of fixed size. And they use monomer dimer model for that. Okay, so this was like an algorithm perspective on sampling with constraints. Let me also explain why sampling with constraints is very natural from a physics perspective. So let me define in some really vague terms what is a ferromagnetic Ising model, and I'll show you what happens with it. So it's actually pretty simple. You take your graph, and every vertex can have either a plus or a minus spin. Right here, they're just like two different colors. And so you have two parameters. You have temperature, and I don't know if you ever try to, please don't do this at home, but if you ever try to hit up a magnet, at some point it will stop being a magnet, right? And that's like a phase condition you can show using statistical physics. But basically, the higher your temperature is, the more kind of independent your vertices are. They don't care about each other's plus or minus sign. But the lower the temperature is, the more aligned the neighbors on your graph want to be, right? So when your temperature is low on the right side, your vertices will start getting, like neighboring vertices will have the same sign most of the time. So they will have these clusters that are connected, right? And there's also a second parameter, and it's called magnetic field. So if you have some strong magnetic field affecting your magnet, maybe your magnet would want to prioritize plus spins. So most of your vertices, like in this case, will want to be purple or something, right? And less of them want to be blue. So now what happens if we just say, no, we want our magnet to have a constant number of plus spins, right? And we only can vary the temperature. So what happens is that now you have a constant amount of, like, say, blue and a constant amount of yellow vertices, like vertices, colors that have to be on some vertex. And now you're trying to minimize the number of dichromatic edges, so edges that will have two different colors. And so what's the way to do it is that it's, put yourself in a blob like that because it minimizes the perimeter, right? So here, this structure is what would minimize the number of your dichromatic edges. And so your most natural state space would look like this. So it's a really pretty behavior from the physics standpoint. And it shows that sometimes when you put constraints, your model behaves totally differently. And there's new interesting things that happen structurally to the model. And I think that's also something we notice in graph theory a lot, right? Like you put a constraint and you get an interesting structural result. So okay, so for us, what we're gonna do is we're gonna work with the Potts model, and it's a generalization of the Ising model I just showed in a way that we allow for Q colors. So before we had two spins, plus and minus, now we have Q spins, and you can just think of them as Q colors. And it has several variations, but the one that's useful to us is the following. So we're gonna say that we have different weights for different colors. So lambda 1 for color 1, lambda q for color q. And the partition function here is a sum over proper colorings. And the weight of every coloring is a product over colors. And the weight of the color to the power of number of vertices of that color in your given coloring sigma. Are there any questions at this point? Okay, sounds good. So let's just play this a little bit. If I make all my lambdas equal to 1, that just means that all my colorings will have weight 1. So I'm just summing over all proper colorings. So this will give me the number of proper colorings, right? If I make lambda 1 much larger than lambda q, what happens is I give more weight to colorings with more vertices of color 1 than color q. So in my Gibbs measure, I would be more likely to get those, right? Also notice that this function is multivariate, right? Because we have like q parameters, and it has like different weights for different colors. So what you also could do is generalize this and put here like a penalty parameter like w to the power of monochromatic edges and allow to sum over all kind of colorings improper too. And most of our results will hold for this, but I don't think it makes sense to define something harder here because this is sufficient for us to get all the results we need. Okay, so what happens is you also can get a Gibbs measure on this, right? How it would work is we have a random coloring, and the probability to get a particular sigma coloring is the weight of your coloring sigma divided by the sum of weights of all proper colorings, which is your partition function, right? That means that if I increase my lambda 1, then colorings with vertex 1 are much more probable. Okay, so probabilities here to make sense, we would need lambda i's to be real and positive, but we can still consider partition functions like to be in the complex domain because we like complex polynomials, right? And here I'm going to introduce a tool that I think is really, really cool. And it looks a little scary at first time, but it's actually like very natural and explain why it's important. So the tool is zero-freeness. So morally, partition functions that we like because they give us so much information about the object we're trying to study, they're complex, like is they're complex polynomials. And A, we know a lot about polynomials, and B, complex analysis is just very nice. So that means let me define zero-freeness first. So you're given a partition function, and we're going to say that a region D is zero-free if inside of this region D, there are no complex zeros of the function. Okay? And so why is that even something that's like natural to define? Well, notice that for us, all the partition functions we've seen so far, they have positive real coefficients, right? Because, for example, they count the number of colorings with a certain weight. And so we cannot have positive real roots of the polynomial. Therefore, we know that at least like the positive real line in the complex domain will be zero-free. So maybe we can hope that around some segments of it, we're going to have like a whole region that is zero-free. So, okay, let me first try to tell you why zero-freeness is a very, very, very powerful tool. And this is going to be the most vague slides of all of my presentation, mostly because all of these tools, kind of deserve their own like talk. But I'm going to try to give like an intuition for all of those tools that you can get if you have zero-freeness. So if you can prove a zero-freeness result in some models using Barbanok's result, you can get a deterministic algorithm that will approximately count your combinatorial objects. Like it would not work for particularly our model, but say if it was, then I would get an algorithm for free from my zero-freeness result that would tell me an approximate number of colorings in my graph, right, in polynomial time, which is just a very nice result to have. Then cluster expansion. Cluster expansion is a very interesting tool that we got from physicists, and it has a lot of different applications and interpretations. But roughly what it gives you an extremely detailed understanding of your partition function, right? And also of your moments function. And what it can do is sometimes you have a lot of dependent variables, but the dependencies are weak. So cluster expansion can help you work with your dependent variables as if they were independent and then count your error terms that come from dependencies, which is very nice, I think, because in probabilistic combinatorics, we often deal with the problems where like independent case is very nice, dependent case is very, very not nice, and we don't know what to do. And so cluster expansion is one of those things where we can get really, really precise results, even if we have a lot of dependencies. And there's kind of a connection here. So Shearer showed that roughly Lover's local lemma holds whenever zero-freeness results holds for hardcore model. And Scott and Sokal have this like 90-page paper that has a lot of really cool things in it. But one of the things that they talk about in that paper is that mathematicians and physicists came up with isomorphic proofs to show Lover's local lemma and zero-freeness for hardcore model. And it's just really, really cool because that really tells you that we should really look into what tools physicists have because they sometimes are bothered by the kind of things we're bothered, and they have tools to deal with the kind of things we want to deal with. Okay, there's also a central limit theorem. To remind you what that means is that if I can show that a number as a number of vertices my graph grows, my random variable, like the size of my independent set, can approach normal distribution. And normal distributions are nice. We know how to work with them. Because the moment we have that result, we can leverage a lot of knowledge about our random variables. Then there is like spectral independence. And I would say in the last 3-4 years, most like fast mixing results in sampling that got really good times like n log n time or n square log n time, they come from spectral independence. And so it's a really powerful tool, and zero-freeness also in some models gives you that for free. Lastly, there's a tool called strong spatial mixing, and it's a very natural sort of observation that tells you, well, maybe I have some probabilities for my vertex V to have like a spin plus one, a plus or minus, and I have some probabilities for my other vertex neighboring to it have spins plus or minus. If they're neighboring, they affect each other immediately. But as the distance between them grows, their sort of dependency on each other decreases exponentially. And that's sort of, and stronger is what strong spatial mixing gives you, right? It sort of also helps you think about some of your vertices as like almost independent, which gives you like more leverage from independence case that you can get. And so I hope that I was able to convey that zero-freeness is a very, very, very cool tool. And it gives you a lot of different applications in that don't necessarily are known for all models, but for some models, you get those for free. So, okay, now that I told you about all this really, really cool tool that gives you so many things, what do we really know about results in zero-freeness? So, Laura Sinclair and Srivastava in 2018 showed this really cool result for univariate plots model. So here you don't have weights for color classes, but instead you have weights for like monochromatic edges. So they're trying to say like, we penalize an improper coloring according to how many monochromatic edges it has, right? And what they were able to show is that given a delta, they can find you balls of radius tau delta all around the segment 0, 1 on the real line. And in the union of all of those balls, it's going to be zero-free. And the only problem is here, the number of colors they require is 2 delta. And let me show you that 2 delta is just really hard to get rid of. Like there's a really recent paper by Banks, Beracal, and Rex, and it's really impressive. And they have to do a lot of new ideas on top and completely rewrite some parts of this proof. And they are able to improve this to 2 minus eta delta, so that just getting like below 2 delta also requires work. And I think there is some sort of symmetry between how hard it was to remove the number of colors for the sampling of uniform colorings, and between how hard it is to remove colors in the zero-freeness region. Okay, and so what our result is if we have 2 delta colors and a delta boundary graph G, in the multivariate complex plane, there exists a ball of constant radius 1, of constant radius around 1, where we have the zero-freeness region, right? So let's think of why 1 is intuitive. So if all your lambdas are equal to 1, you're just basically counting Q colorings. So your partition function is equal to the number of, Q colorings. Since Q is bigger than 2 delta, you have at least 1. So your partition function cannot be 0. So it makes sense why it's non-zero at 1, and that kind of gives you some hope for trying to prove that there will be some constant radius around which it's not 0, but it's not that easy. We have to take a lot of methods from the Lower Sinclair Sevestavas paper. Okay, and so that is basically the result we have, and I'm gonna give you like a very hidden under the details taste of the proof, and show some of the pretty ideas, because I feel like whenever you have to deal with complex analysis, even though it's complex analysis, it's heavily influenced by the graph theory part of it. Okay, so we're gonna define a function, ZGVI, to be a partition function like before, but in this particular case, we will pin the vertex V to have a color I, right? So that means that your total partition function is just the sum over these cases when V has a color 1, V has a color 2, V has a color 3, and etc. Right? And what you can show is that like all of these things are complex points, right? And if the angle between them is small, then their sum cannot be 0, right? Because they're imaginary parts which does not cancel each other. So the way that you can trace their angles between them is you can, for example, take their ratio, right, of those, of like any pair of partition functions. But this ratio also has a really nice combinatorial interpretation. It can be interpreted as the ratio of marginal probabilities of vertex V to be I, divided by the probability of vertex V to be colored J. So that's nice to work with. And the proof is going to be an induction over the number of unpinned vertices, meaning the vertices we didn't color yet. And it's kind of counterintuitive because actually, like, we're gonna be saying that like we can prove something when all vertices are pinned, and we're gonna be like, and we're gonna be going like a step up every time. Okay, so it means that for our like reduction step, we have to somehow like show that a graph with like some number of unpinned vertices, we can reduce to a graph with a smaller number of unpinned vertices. And I'm gonna hide a lot of details under the rug, but what you can do for that is you can use this like non-trivial construction of that works like this. You have a vertex V, which is not colored yet, and it has D neighbors like U1, U2, UD. And what you can do is you can make D copies of that vertex, and you adjoin each of the copy to each of the neighbor. So like V1 to U1, V2 to U2, etc. And then you color the first K minus ones with color I of these vertices. And then you color like all the ones after the case one to the color J. And then you kill this one. So, and everything else stays the same. So what just happened is we did increase the number of vertices, but actually all of these vertices here now have a color, and this one didn't. So this graph has less unpinned colors. And so we can use the inductive property of that graph. So very roughly, we can write the ratio that we talked about before as some function of marginal probabilities in this graph. And that basically gives us the proof. The proof is like 16 pages, so like, it's not going to be really easy to like transmit over a talk, but I hope that you understand that there's like some graph theoretical prettiness in the complex analysis proof. Okay, what are some other tools that we have is, for example, central limit theorem. So to remind you what that means is like, you want to show that as, say, for example, the number of vertices in your graph increases, the random variable distribution converges to the normal distribution. So you can use the properties of normal distribution. And there is a really powerful theorem by Michelin and Sarahas-Boutet, which says that if your random variable takes natural values and 0, if you have a probability generating function and it does not have complex zeros, then you get central limit theorem. So, and you have to get some lower bound on the variance here. So what that really means is you have zero-freeness, you have a lower bound on the variance, you get central limit theorem. What the caveat is that this theorem is for the uniform variables. And for us, what we want our random variable to be is we want our random variable to actually be a random vector where like each entry is a color class size, right? And so now we have to find ways to sort of work with the multivariate random variable. So what we do is we say the following: let us take a direction like C and take a linear combination of color class sizes. So we're just going to take the dot product of C and our random vector, and that's a univariate variable, and we can show that our zero-freeness gives a zero-freeness to that univariate variable. And then on that, using the previous theorem, we get a central limit theorem. And if we can do that for a dense number of different directions C, and for each of them you get a central limit theorem, that means that for your random vector, you would also get a multivariate central limit theorem by some really cool theorem of this Gauss-Legere-Manda. And so that's how you get a central limit theorem. Okay, so are there any questions by now? Good. So forget about all of that. Let's get back to like pretty globber. So we did globber before, but now we have weights for different colors. Let me explain how do you generalize. Well, it already existed, but you have to basically do this for different weights of colors. So what you do, you start with a proper coloring, and on every step, you choose a vertex in your formula at random, and then the vertex has to pick an available color randomly, but now not uniformly. Now we want to say, pick a color I with a probability lambda I over the sum of different lambdas, right? Because in this case, our globber would be more willing to give more probability towards the colors that have a larger weight, which is what we wanted, right? And you can actually show that the station distribution of the weighted globber is a Gibbs measure of our Potts model, which just basically means if I run this globber long enough, it will give me a distribution that I defined for my statistical physics model that I defined before, right? So this works great. And so what that gives us is it gives us also that colorings that have same color class sizes, their weights are only defined using color class sizes. Therefore, their weights are equal. So this globber would give those colorings an equal weight, right? Not all colorings would have an equal weight, but the ones with same color class sizes will get equal weight. And lastly, how do we wrap up everything? Is we do a single rejection sampling. So what we do is we have to choose a lambda such that the expectation of your random vector of color class sizes is your n vector you wanted for your n coloring. And so what we're going to do is we're going to say, look, we have central limit theorem. Using a lot of tricks, we can get a local central limit theorem, which just tells us that not only the distribution converges to normal distribution, it converges pointwise, which means that the probability of our expectation value to appear in like a random sample is at least inverse polynomial, because that's what it is in like a multivariate Gaussian. And that's great, because what that tells us is we can have a really simple algorithm. It just says, run globber for n log n steps, and then look at what coloring it gave you. If the coloring is the coloring with all the class sizes you wanted, keep it, output it. If it's not the color you wanted, throw it away and repeat global again. And the point of everything we just did with the local central limit theorem is that you won't have to throw out too many of those, because in some polynomial number of repetitions, you're gonna get your expectation. Okay, I hope that made some sense. And if it didn't, here's basically a diagram of how our proof worked, if you want like a bird view picture. So we have a zero-freeness proof. It's probably like the main part of our proof. And it gives a central limit theorem, somewhere in the middle here, which gives us a local central limit theorem. And then using the existence of appropriate lambdas, which is something we're still working on, and also the fact that global dynamics runs fast, I didn't show you that step. It uses fast coupling technique. You can get rejection sampling to work. So basically, it's the algorithm I just showed here, where you run global, throws things out. Okay, so that was the proof outline. Are there any questions? Okay, cool. So even if you got lost somewhere in between details of the proofs, it doesn't matter, because I feel like even if you don't like algorithm, statistical physics, there are still some really pretty conjectures that we think should be true that you might like and you might know how to solve. So here's an example of one. We think it should be possible to prove something of the following taste. Uh, if all of your color class sizes are less than n over delta plus 1 floor for all colors, then if your maximum degree of a graph is delta, we think one should be able to show that the graph G is n-colorable. And it's not the kind of graph theory I do, so I don't really have ideas for how to approach that. So if you do, let me know. And I think that this actually can get a little bit easier, because for the kind of things I care about, because I have to use zero-freeness, I need to use at least two delta colors, which means that you also can look at, the subcase of this conjecture for when the number of colors is bigger than two delta, and maybe it can give you some flexibility in how to, throw around your colors. And so the conjecture we make in terms of sampling is, we think if we have more than two delta plus 1 colors, and your color class sizes are less than n over 2 delta plus 1, then you can probably get some existence result for those colorings. And we can probably find some lambdas for which this works, where there would be a polynomial time approximate sampling algorithm to sample those n colorings. So this is what I think should be true. And I guess it really depends on like how much one can push the boundaries of what we know, like in terms of like, can we prove this for all such NIs? Maybe there's a counterexample I'm not seeing. For some of those cases, maybe this is true, but you have to have a stronger restriction somewhere. So that would be really interesting to see. And I feel like there is a lot of some sort of like hidden correspondence between the kind of things you could prove existence for, and the kind of like and like the part where it should be probably easy to show the existence should probably also be the part where it should be easy to show sampling, right? Those usually go hand in hand, and it would be really interesting to see what people can prove. So yeah, that was everything I had. Thank you so much for your attention. I'll be happy to answer any questions.
But first, why don't we unmute ourselves and let's thank Aiya. Okay, are there any questions? Maybe people are shy, but I do have a question. So you'll have to forgive me because I'm awful at complex analysis, but I remember a long time ago when I took analytic number theory, the reason they were worried about zero-freeness of the Riemann zeta function is essentially they wanted to look at the reciprocal and look for poles. So does that have any does that idea of looking for poles of the reciprocal have any influence over why zero-freeness is important
Uh,
for this partition function?
Well, to be honest, I don't remember much about poles. I thought poles is where your function is like not well, not well, like it's not well defined or something.
Yeah, it's like you're dividing by zero.
Oh, okay, okay. So I'm not sure about that. The one thing I can tell you is that like there are results that say if you're in a zero-freeness region, um, it means that the log of your partition function is analytic.
I
And
see.
that means that you can write a Taylor expansion of it. And
Okay.
that sounds like very random, but what that really means is if you have a Taylor expansion that we know that the terms in it will decay. So that means that I can stop myself at some point and say, this is a good enough approximation for me. And Taylor series are really easy to count. So basically, anytime you have zero-freeness, it means that I can approximate to any value I want just because it's easy for me to count the Taylor series coefficients. And the other thing is, if you have, like, I know very little about this part of research people do, but some people do research where they say, if you're very close to a complex zero, it is NP hard for you to do anything. So the intuition is like you're far from there, everything's good. You're close to zero, everything's really bad. Roughly.
Okay. So would it be correct to summarize really, really roughly as if you have a zero-free region, then it's safe to take the log?
Yes.
Okay. And then you can get a Taylor series of the log function, and then lots of nice things happen. Okay. Thank you. Do other people have questions? You could also type them in the chat. All right. Then thank you again for that wonderful talk, Aya. All right. So, Azulfan, do you have a
I don't
question?
know. Nothing. Just to say thank
You.
Okay. And why don't I stop the recording now?